let's get back to the problem we were doing, right? So very quickly, where I defined right and left going modes, and we can do that for the nonlinear case also. And actually, these objects have a nice name. They're actually called Riemann invariants. So Riemann with so many important things related to his name. So let's see what is a Riemann invariant. I'll mention a little bit what it's useful, but also it's useful in many ways, and I'll just mention it, giving you keywords, even though I won't do everything that you can do with Riemann invariants. Okay? So let's go back to the problem we were. So let's go to the shallow water equations. Let me write it in matrix form, already with a flux function psi. Okay. So this is definitely a problem of this form. Let's see what the notation I used was B1. I don't know why I put B1, but let me just put B. Right? As we did before. It's a system of hyperbolic equations. Why? Because we have that lambda is equal to minus the shallow water speed, which is this if the bottom is varying. Right? So that you remember the picture, and I mentioned about a tsunami, and the shallow water model. You will see later on in the course scalings like this. So where lambda is big, so it's a long wave model or a shallow water model, and where H0, H0, is a characteristic depth. So I'm not even going to write it, okay? Because I'm going to come back to this later on when I do dimensionless analysis in a few classes. So this is like a typical depth. Could be, the average depth. So we have an idea. Oh, the depth goes from minus 4,000 meters, like for a tsunami, to 3,900 to 4,050, right? So H0 could be the average, for example. Okay, this is the shallow water speed that I mentioned that tsunami can go really fast, right? Fine, but now let's go to technical stuff. Okay, very quickly here. Oops. Oh no, but last time I was doing the acoustic problem. Okay, fine, no problem. Sorry for my mistake. So now for the acoustic wave, it works for both of them, but I was checking out the notation, where's the Z, right? It was because I was doing the acoustic one, so sorry. So for acoustic waves, okay, so let me write it like this, because you can see in the last class. So for acoustic waves, we used, the travel time variable, x, 1 over the slowness, which is the speed of propagation of the wave. And that allowed us to rewrite our system, excuse me, in the form, okay, now I'll jump to where we were. Where zeta is called the impedance. Okay? And you'll see that it plays a role in reflection of waves. And let's see, I did one more thing. And moreover, so let me see if the story is telling us, okay, for acoustic waves, we used the travel time variable, this guy. I showed you that this has units of time. And that allowed, this variable allows us to rewrite our system in this way, with two times, right? I call this the clock time, which is just the standard time, and the travel time, which we understood, okay? Now, then, let me put it like this. We got that. This is where I think I stopped, which is the right and left going modes. Okay, attention here. I think I forgot this 2 last class. Okay, so it's good it's recorded, but no big deal because what I said was correct, but I forgot this 2. And this is called the reflectivity. So look at this. Let me give you the intuition and why I like this. This is where I stopped last class, but I was rushing because I knew I would come back to this today. So the thing that we have are piecewise medium. This is a pressure wave coming down for the acoustic problem, okay, in the, right, the crust of the earth, for example. And as this wave comes down, excuse me, when it goes, okay, from a medium, let me exaggerate. This is the rapidly varying case, which is more difficult. Let me do a different picture for you. Okay, so this wave is coming down, and we're actually going to do by hand a case later on in the course, because related to some interesting things of papers that I might give you to read and so on, which I did last course, is that when this wave gets to this interface, say these are 2 different types of rocks, okay? So think, which is good for intuition, that the white rock is harder than the orange rock. So this pressure wave, which fits in this slab, this is called the slab, uma camada, a slab. It propagates as a traveling wave. It doesn't change its form. It's a wave in a homogeneous medium. The coefficients are constant, right? So this is a better example. Good, I'm coming to this. This is a better thing than I was doing last time. So then, like this looks nicer. So then, in region 1 and region 2, okay? So in region 1, look at this. In region 1, this guy here is 0, because this guy here is 0, because the impedance, right? I wrote last time, I should write it here again, which is, here it is, let me see, yeah. Rho kappa, isn't it? I always get it wrong, yeah, because the speed is rho over kappa. Okay? So if the density and the bulk modulus, where the compressibility is 1 over the bulk modulus, bulk modulus is like an elastic property of the medium, okay? So if this is constant, right, here in the orange region 1, if this is constant, this is 0, okay? If this is 0, I have a downgoing wave, okay, and a 0 upgoing wave, because my initial data is a downgoing wave. Okay, so since this says the z direction, if you like, we can think of A like this and B like that, which would be right going and left going, as I mentioned before. No mystery, right? So this is cool. This is cool because if the reflectivity is 0, pointed wrong, because the impedance is constant, right? So the derivative is 0. The impedance is constant because the density and the compressibility don't change. We have the most simple wave equation that I presented in class 1, which is a downgoing wave. And because there's no information in the beginning for anything coming up, B is 0. Okay? Now, when there's a jump discontinuity, and we will see this, right? If there's a jump discontinuity here, this guy is going to be like a delta function, right? Because the derivative of a Heaviside function is a delta function. We will see this. Actually, when I talk about weak derivatives, we'll see this in more detail, but we kind of know that. So, even if you're a little bit like, okay, André is going to put a Dirac there, just think that there's a very fast transition from one, which is what a discontinuity basically says, right? A so fast transition from one region to the other that we collapse that to a line. But just think it's a smooth transition, almost like a hyperbolic tangent scaled in a way that's very fast, so that we don't have, oh, this is not a delta function, don't worry. But there's going to be a reflection, right? It's just like I mentioned, the echo. If there's an obstacle, my voice goes a little bit to the other room, and part comes back. So therefore, here, at this part here, at the yellow interface, the orange interface, which is this line here, we'll see this in more detail later on, there's going to be a reflected wave, okay? So therefore, part of the energy of what was going down will come back up. And for oil exploration, that's the important information, because that tells you what the properties are. Whether you want to do the imaging problem, which is just to see a little bit like you see a tomography of a baby, whatever, you see where the reflectors are, and then a specialist may say, oh, maybe there's oil here, or even something even more sophisticated, which is the inverse problem, which is calculating the properties of the speed down there, okay? Anyway, both are a class of inverse problems. One is just finding where is imaging, right? To find the image of where the reflector is. The other one you find not only where it is, but properties, right? What's the speed and so on. So this is the place where reflection takes place, and it's clear here. Because A is going to travel down, and suddenly it's going to generate a B wave coming up. And vice versa, and the B wave also, from the mathematical point of view, nothing prevents me from exploding something from down there and also having a B wave coming up. So these are, as I indicated here, a right and a left going mode, or in this problem, an up and a down going mode. And if the medium is homogeneous, they are decoupled. Right? One doesn't see the other. But if the medium is heterogeneous, because the reflectivity of the medium changes, they couple. Okay? So, another important thing. These guys here, they're like constant, but notice that I change variables. So they're constant along characteristics, because this is the same thing as total derivative of A with respect to T is equal to 0 if the medium is homogeneous. Okay? So this is a first example. I'll give you another one very soon of what's called the Riemann invariant. I won't even write this here. A Riemann invariant is an object, and it's very useful, that is constant along characteristics. So if the medium is homogeneous, A is constant along one characteristic, and B is constant along the other characteristic. Okay? And even in the papers I've written where the medium changes, whatever, we tell the reader, well, we're going to abuse of language and say that the Riemann invariant varies slowly. I mean, if something is invariant, you can't say it varies, but because it's a well-known object, we say the Riemann invariant, say if this r here is small, is an epsilon, it varies slowly. So it's just jargon, terminology, but no big deal. Okay? But in essence, these are right and left going modes or up and down going modes, and they're very important for me because I can keep track better with these modes of what's happening in the dynamics right and left, okay? And I didn't write here, but I'll leave it to you that basically from A and B, I wrote it last time, you can, after you solve this problem, you can recover U and P, okay? Just check the notes. You're going to see. I'm not going to write it here for the sake of the blackboard of space and time, okay? Okay, so let me write what I just said. That's important so that we keep that registered. So when the medium is homogeneous, the modes A and B decouple. So in a very sort of a condensed notation, I can write this. See if, without me explaining, if the notation speaks for itself. Excuse me. Does the notation speak by itself? Right? This is saying that A is constant along the right going characteristic, which is dx dt equals to 1, and blah, blah, blah. B is constant along the left going characteristic. What is the left going characteristic? Dx dt equals to minus 1. Notice another benefit. At one point with one graduate students, we were doing some things with waves in random meter, whatever, and actually solving the problem numerically for A and B was also interesting. Why? Because the characteristics are plus or minus 1, right? So on a grid, numerically, it's just things going plus or minus 1, where the original characteristics are crazy, are varying because the medium is varying. So somehow with this strategy, we sort of not only see right and left going modes, but we have normalized the characteristics, and the variable medium information went from here, from the eigenvalues, which is not this the eigenvalues, right? But if you find the eigenvalues, to a forcing term. So you sort of mathematically relocated the information of a variable medium. Okay, just mathematically, this might be convenient for some situations. And here, you see, the characteristic is plus or minus 1. Here, the characteristic is not plus or minus 1. It will depend on zeta. But the problem is the same, it's equivalent, right? So use it in the way you like. Okay, let's look at a nonlinear problem, shallow water problem, and then let's see, I'll mention about the Riemann invariance for that case, which first I'll do it, as I mentioned last time, using a trick, right? If I had never seen this as a guy, how would I invented this trick? It's basically out of trying many times, I don't know, out of experience. But then I'll also show it the way, which is the systematic way, if we hadn't identified the trick. And it's good, of course, to know both ways, because tricks are good to know, right? But they should not be mysterious. They should be, right? Okay. So first, as a comment, in 2x2 systems, because in higher order systems, this is not possible, so in 2x2 we can guarantee. I'm not going to show this, but just as a fact, in 2x2 systems we can find, let me call it this, these objects that are constant, therefore invariant, along characteristics, right? And these are therefore called Riemann invariance. Okay, so let's see now the shallow water case with a trick. Now here's nonlinear shallow water equations. We saw the linear one, now we're going to see the nonlinear shallow water equations. Written in a slightly different way. It's good because then you see different ways of writing a problem where capital H of xt or in this case I'm doing the constant depth, okay, H naught. So basically the problem is like this. Okay, so capital H is the total water height, right? You will see, I'm going to show it to you a little bit, but in the fluids course, we see that in all detail that when the problem is linear, we can put our conditions on this dashed line. When it's nonlinear, you have to compute everything, blah, blah. So there's some differences. You can linearize in a systematic way. I will do this later on, but not now. So if I were to linearize this, this guy would fall out. There's a nonlinear term here, which is u eta, which falls out, and we get that other equation we saw over there. Okay, no big deal. Now, this is a nonlinear problem, which means that when the wave height is, so the problem is nonlinear. Well, let me put, so if this is a typical amplitude, right, the problem is linear when A over H naught is much less than 1. Basically, you send it to 0, which means the amplitude is negligible with respect to the depth. Excuse me. So this is when the problem is linear. When the problem is nonlinear, this guy can be an epsilon, but it's different from 0. Okay, so basically linear is the limit as this goes to 0. Okay, so why am I saying this? Because this is already a regime where then the tsunami, if it's a tsunami, is getting closer to the shore because the depth is going down and therefore the amplitude is getting higher, right? And therefore, this wave can break in the style of Berger's equation. So remember that I mentioned to you, and actually I sent you some material, you'll see pictures, is that this is the way Berger's break. Let me put it like this. Berger's breaking, and this is the way wave breaking, which we'll see in the near future with potential theory. I mean, we are not going to see the wave breaking. We're going to see potential theory in the model that will lead to that, okay? For us, there's no time to, these are some things I mentioned a little more in the fluids course, but not here. And still, you have to do this computationally. Okay, so different PDEs, for similar applications, you have to decide, well, do I want my wave to break like this, or do I want my wave to break like that? It depends on the application. If you're doing, for example, a flood wave in a river, which breaks very quickly, this might be a reasonable model. If you're looking for waves in the ocean, for like an impact of a wave on a wall or on an offshore structure, you have to see this one, because actually this guy plunging, as it says in English, generates a very big impact, much more than just a broken wave and so on. So depends on the model, okay? So here, this is going to break. And can you see here, it's not Berger's equation, but you can see a Berger's equation like nonlinearity. For example, this term here just looks like Berger's equation, right? In here, there's also a little bit something that looks like Burger's equation and so on, because the H has eta, and the U it's nonlinear, so, but it's more complicated. Okay, so now let's see how we get. Okay, now let's see how we get the Riemann invariance for this guy, which is nonlinear, right? There's a trick to quickly get the Riemann invariance from this guy, and then I'll show you the systematic way, which is more lengthy and so on, but it's good to know. Okay, so this is our goal as our exercise. So I think I never mentioned this. Well, maybe I did, but very quickly. So let me mention, it's very important to mention this. In conservative form, we have that. Let me use this space here. No, I'm writing the other ones. Come on. I'm looking at the wrong place. Sorry. So this is the shallow water equations. Let me drink a little bit of water. This is the shallow water equations in conservative form. Okay? Do you know why this is called in conservative form? To some extent, I already mentioned this. Of course, I mentioned it in a way that maybe you should not, it was in a slightly different sense, you should not maybe connect, right? But I will not do the details here, but I will see in your faces the expression. Remember when I wrote, remember better, let me say the best keyword. Remember when I deduced the Hankin-Hugoniot condition for how a jump travels and so on, and I said, well, the best way to do it is, well, let's start with a system written in divergence form. So there was an S and there was an R. Here's an S, here's an R. Remember, right? And I said, okay, to look at a jump, a discontinuity in the solution, we don't want to use the differential form. We want to use the integral form, because it's much better to integrate a jump than to differentiate a jump, right? Singularity is better to integrate than to differentiate. Now, I'll just say it in words, as I usually say, like we're talking to colleagues in the corridor, and we don't have a blackboard, and then I'll continue. So this is in conservation form, because if I integrate this sort of in space, right? Remember that I got something that was dt of an integral is equal to the flux on the boundaries. That's how we deduced the Hankin-Hugoniot condition, right? But if the flux on the boundary is 0, it's not that one balances the other. That's a balance law. When it's really a conservation law, the things are conserved, either because the extremes of my interval are so far away that there's nothing happening there, or there's no flux. I mentioned to you that there was a total mass that did not change in time. It was ddt in integral of blah, blah, blah equal to 0. That's why it's called the conservation form, because it's exactly like it's written here. But for our sort of classwork that we need to do right now, right, it's best to write it in non-conservative form. So let me write it in non-conservative form. So and you immediately see why. And that was the one that by mistake I was writing before. This is exactly the same PD. Okay? So let me make another comment that I'll maybe mention in this course just once more, the comment, but not much, because this course is not numerical. If you want to do a numerical method that is what's called shock capturing and so on, it's better to solve it in this form than in this form, right? This is like a cultural comment, like, right? I want to explain why, I won't show why, but as a comment. Now, for what I want to do right now, this form here is better, because now this is non-conservative form, so this would be the flux function, and here I got this matrix. This is my matrix A, but now, or in our previous notation was B, so let me write as B. I don't think I have it in the notes. Doesn't matter. This is our matrix B because we have the matrix A here, the matrix B. This is the matrix B, but it depends. Of course, it depends on X and T, but more importantly, it depends on U and H, which are our unknowns of the problem. That's why the problem is nonlinear, right? But still, this matrix is ridiculously easy to diagonalize. Okay? So therefore, we get, eigenvalues of B are like this. Let me skip, right? It's so easy, you can do it. Well, I'm putting as dependence of X and T, but in the notes it's only of X, but it could be X and T. So let me write like this. Okay, the note I put, I think just to call attention, it was X of T. It varies in X. So it's equal to this, which I can also write like this. And which I can also write in fluids. We sometimes useful to write like this. So a little bit of a fluids terminology. What am I doing here? Nothing deep, okay? So what I'm doing here is this. Let me maybe isolate this. This is the eigenvalues. Very easy to calculate from there. They're distinct, so the system is strictly hyperbolic, independent of what the solutions are. I don't know the solution. I don't know yet U or H, but the matrix is trivially diagonalizable, has two eigenvalues, real eigenvalues. Remember that the shallow water speed was GH0, but now the H is changing, so basically this is the wave speed, okay? So this is the wave speed. To some extent. U is a little bit the speed related to the fluid, and if you pull this Cx out, you're going to get this F here, which is U divided by C, and this ratio of speeds, is called the Froude number. And the Froude number here might play the role kind of similar to the Mach number in gas dynamics. The Mach number has to do with supersonic flow and so on, right? Supersonic flow is when the airplane has Mach greater than 1. So here in fluids, when the Froude number is smaller than 1, which means if the Froude number is smaller than 1, let me maybe write here, it means that the flow is slower than the wave speed. If the flow is equal to the wave speed, it's critical. The Froude number is critical. It's the similar thing as you're exactly at the border of a supersonic flow. You have Mach number 1. And if Froude number is greater than 1, you call it a supercritical flow. Supercritical flow is kind of an analog of supersonic flow, which is Mach number greater than 1, okay, which is greater than the speed of sound, right? That's what supersonic is. And look what happens. Is that if depending on these ratios here, here it's better to see, depending on the Froude number, if we're in the subcritical case, the Froude number is smaller than 1. So you have a right and the left going characteristic, just like in the linear case. But if you're in a supercritical case, fruit number greater than 1, you have two positive characteristics. So everything's going forward. There's nothing going backwards. Right? So you see how sometimes using a reference number, or later on we use also dimensionless variables. Here it's dimensional. You get sometimes a number, a parameter that tells you in what regime you are. So I'm already preparing. We'll talk about regimes, what I mean by regimes. Later on when we see a dimensionless problem, in particular, a good exercise will be when we do potential theory, which will mix elliptic equations with wave problems. Okay? But you see, now the nonlinear problem already brings a novelty, which is maybe the characteristics are both going in the same direction. Right? Just as a comment. Okay, now let's go. Got to keep track of time because I want to speak some things today. Let's see how we can get now the Riemann invariance, not in a systematic way, in a tricky way, but it's good to learn tricks, okay? So, for convenience, write the system excuse me, in terms of of C of x, where dC of x is equal to G and this is so that if we differentiate in time or space, we know how to sort of change variables. And then, okay, skipping the calculations, we can then write the shallow water equations as okay, this is just simple calculation I'm skipping, doing this change of variables. Okay, and then you say, what have I gained? Well, nothing, but they're kind of looking the same, these equations, so add and subtract, and this is what comes out. Excuse me. And this is nice. And this is nice. Why? Let me, as I get this, let's see. Why is this nice? This one with a yellow marker there. Why is this equation? This is the same equation as before. Now written in terms of U and C. But why? What is interesting? Right? Let me exercise with you to the critical sense. Why? What is the interesting thing here about this equation? Why I'm celebrating that I got to this point? In words, right? In words. Look. Let's see how I would sort of celebrate this. Look, let me make it like this. Let me put yellow here to highlight things. This looks like a derivative in some direction, right? And this is a guy which will not change under this differentiation, right? So therefore, these are the Riemann invariants for these characteristics. Okay? Look at this. Just like the first class we saw. If dx dt is equal to u plus c, this is the total derivative in time. Just like we did in the first class. Now, if the other dx dt is equal to this is also a total derivative in time. Right? So this is a characteristic, this is another characteristic, and for this characteristic, this guy does not change. And for that characteristic, this guy does not change. So those are the Riemann invariants. The guys who do not change along these characteristics. So therefore, those are the sort of, in this sort of coordinate system of the characteristics, if you like, these are invariants, and therefore these guys kind of can give me the right and left going modes depending if these characteristics, to which direction these characteristics are pointing. And if they're pointing both forward, like in the supercritical sense, it basically tells me what are sort of quote unquote the modes related to that characteristic. Remember the last time I was playing with characteristics and saying there's like many channels of information in n dimension coming to a point, right? Here there's two channels of information because there's two characteristics, and on each channel, quote unquote, there's a guy who doesn't change, even if the orbit is complicated. This is the guy that doesn't change. And that's useful. Okay? So let me write this down, okay? So conclusion, let me keep it here, so because of the video. And my sort of caricature, schematic picture in the notes is something like this, right? They don't necessarily have to go back and forth, but so these are the crazy characteristics. And along these characteristics, A and B do not change, okay? And, okay, I have a comment here. Yeah, but I think there's something I haven't written in the notes, and something that I think we will not see in the course due to the lack of time, but when we use characteristics and Riemann invariants, sometimes it is useful. There's a terminology that goes like this, which is not only with characteristics, but hodograph transformation. I don't think we'll see this in the course, but it's important to mention so you know it exists. Hodograph transformation is sometimes transformation which in scenarios like this is useful, where, well, let me ask you, have you ever heard of hodograph transformation? No, so that's good, right? So hodograph transformation is when you mathematically can play a very interesting trick. Not only, you got to see when it works, which is you make the dependent variable play the role of the independent variable. You sort of switch roles, right? And here, let me give you a feeling so that you can sort of believe this, is that sometimes you can use the Riemann invariants as a system of coordinates, right? Because this guy is constant around here, constant around the other one. And so so you basically can think of a curvilinear coordinate system here based on the Riemann invariants, right? The Riemann invariant is constant along this orange curve, but it's another constant over this other orange curve, okay? Similarly for the blue one. And there are situations where you can make use of that fact and use the dependent variables as coordinate system, and the problem simplifies when you change the roles, okay? This is the type of comment that I call in the course cultural comment, that you know, oh, it exists, it's useful, it has happened in my life. I've heard something many years before, and I say, oh, that's what the professor told me, and now I have to study this and learn, okay? So it's good to have in the back of your mind. So this is what autograph transformation is. And for example, with Riemann invariance, there are problems where it is useful to change the role of the objects, okay? I will not explain exactly why, but it can happen. Oh, here I have a comments, which is something I basically already mentioned. Okay. So now let me do, excuse me, how would we get Riemann invariance without a trick, right? I mean, if I were with this system here and I had no experience, why would I decide to change variables to C unless I have tried many things with the problem, right? But after you do that, so it's good to know the trick. But let's see it in a systematic way. What is behind Riemann invariance? So that you also have more or less know the text I'm following. This part here is actually in the book that I said that was not very good to study. It's an excellent set of examples, but actually in DebtNet, this part I'm presenting now is well explained. I mean, he puts it in detail, because some other parts he shows many interesting things, but I think sometimes you've got to have a little bit of a experience, right, to follow. Okay, so this is the presentation in DebtNet. So take a 2x2, strictly hyperbolic system, and I'm write it with our standard notation. Okay? Very good. So, let me also point out the notation, just to make sure it's obvious, but it's good because I'll need it. These are the coefficients, okay? And now, consider the left eigenvectors of A, okay? I'm going to call it L1 and L2. Right? It's strictly hyperbolic, has two eigenvalues and two linearly independent eigenvectors. And the left eigenvector of A is basically the eigenvector of the transpose, right? But you basically hit it from the left. Okay? All right, so let's do this calculation. Okay. This is a similar calculation to some extent of what we can do with the I indicated to you for the linear system to sort of decouple the equation, right? You put it the eigenvectors, blah, 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 and you eventually decouple. It's basically multiply. When I mentioned to you, remember, multiply by the modal equation, which is the one which has eigenvectors as a column. Okay, so if you do this, we're going to get this. Okay, which is equal to, I'll skip one part of the notes. Okay? So maybe I can write this like this. And we have that. I have to put more information here. So see if this makes sense for you. You know, I'll help you with one thing if it's not totally clear. Excuse me. So what have we done here? We got our PDE of interest, okay, and I'm hitting it from the left with the left eigenvalue, which is the eigenvalue of the transpose, right? So therefore, very simple, LA will be lambda L, because it's an eigenvector, okay? Then you reorganize it simply like this, and what we will conclude is basically written here, which is writing the equation in characteristics so that it looks like an OD, right? So here what we're saying is that this thing here, right, can be read as L1 du dx equals to 0, and the other one is L2 du d eta equal to 0. Well, right, this is dx is for the first eigenvalue, this one's for the second eigenvalue, and what the hell is this c and the eta? That's the only thing that maybe is bothering you. Just remember that for the linear case, let me put it here, if you were in the linear case, we could have this c which basically is this. Right? Right going characteristic, left going characteristic. So this, remember that I mentioned to you that actually sometimes in a numerical problem, it might be interesting, more interesting in solving your problem in the yellow coordinates than actually in the original Cartesian white coordinates. In particular, if you have Riemann invariance, it means that a guy that's here will be the same value here. Right? So, because it propagates without changing. So, what this eta and this c are is just, they're constant, but now they're not necessarily straight lines. Right? It's like level curves of this c. So it's like a new coordinate system, right? As I had a little bit here, right? When I do the hodograph transformation, right? So this could be something constant, the characteristic, but if I do the hodograph transformation, I'm going to say that the a and the b are constant. I'm going to use the fact that a and b are constant there. Here I'm not doing hodograph transformation. I'm just saying, well, see, let me explain better. I'm not happy with what I'm saying. So here, for example, the value of this guy, I think there's somewhere in the notes it's written like that. This guy here is C2, right? Because it started from a different position in X. It's this guy, but with a different position in X, right? So these are two different values, two different lines for C1. So it's like a coordinate system, right? So what this notation here is saying is that this U is not changing. It's a Riemann, this is an equation already pointing out to me that I can get a Riemann invariant which is not varying along that coordinate system, which is one of the characteristics of the family of the characteristics. And the other one is a guy who does not vary along another coordinate system of the characteristics. That could be quite complicated, right? Here it's very simple, right? So now, it's just getting conditions. What I'm going to sketch to you, which has to do with, like, in ODEs, we learn about if it's a total differential. So it's basically ODE, it's easy to integrate. Oh, if it's not a total differential, maybe we can put, sometimes we recognize an integrating factor that we multiply, and then it becomes a total differential, right? So the notation will look a little complicated, and it's called, of course, it's a little more generic, so sometimes it might be hard to solve what I'm going to present, but in essence, it's this. It's just trying now to see these as ODEs and thinking, how would I write it as a total differential? And then if I integrate it, sometimes it might not be that easy, but if I integrate it, then I get the Riemann invariant. Because the total differential, right, if I integrate, I know what the U is for this guy, and I know what the U is for that guy. Okay? So that's basically the recipe for for this. Okay, I did a drawing. Look, in the notes, let me put I didn't even notice, but in the notes I did this schematic drawing like this. So this is the C plus, and this is how the Xi varies. This is the C minus, and this is how the eta. It's like a constant eta. Okay? All right, very good. Let me finish with the Riemann invariance. Yeah, I'm going to have a little bit of time to start second order PDEs. At least get things prepared for next class. So then, right, formally, it might not be easy, right, but formally, integrate these two ODEs. When, or if they are, or okay, when they are an exact differential. Okay, so basically the ODEs look like this, right? So we have two ODEs along this guy. Right? And that when there's exact differential, so just so you can connect with, say, some, even introductory books in ODEs have this, things can be written like this. Okay? And then, it's like an exact differential, blah, 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 and you can integrate, or sometimes use an integrating factor. So let me write it and then And if we can do this, these would be the Riemann invariants. So let me mention, right, I wrote quickly and a little sketchy, right, because we don't know if we can do this all by hand. So those two ODEs that were out there, we can write it like this, right, using the components. Okay, so just look at exact differentials, for example, in an ODE book, right? If these are related sometimes to a gradient of something, right, you can integrate. This is an exact differential, so you just integrate. Chances are it will not be, so sometimes you can multiply it by a mu, the first equation, and mu tilde, the second equation, right? Just like when a common integrating factor is an exponential, right? That's the first one that we recognize. We put an exponential. So if you multiply this and this by a mu, and you integrate, and this looks, right? And it looks, before you integrate, it looks like a exact. I'm tripping on my tongue, so let me repeat. So if you multiply this first equation by mu, and then it looks like an exact differential, like we multiply by e to the ax, whatever, right? Then, if it looks like an exact differential, you integrate it, right? Because it's an exact differential, you know how to integrate it. But because you're integrating it along C+, the constant of integration depends on the eta, right? If you're integrating on the other characteristics, right? Because then the constant of integration depends on Xi, right? And these will be your Riemann invariants. So see, it's a complicated, it's a systematic, more complicated way. That's why the tricks of adding and subtracting is a shortcut that's good to know. But, right, if you hadn't guessed that, you have to go through the whole process, integrating, blah, 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 getting to these ODEs, because after all, characteristics look like ODEs, right? But the constant of integration is only in one of the variables, right? So it's not a constant. It depends on the other guy. So that's it. Okay, so that's the way we know. But actually, when we use Riemann invariants in the problems, more complicated problems later on, there are going to be these 2x2 cases like A and B that I showed here. Nothing much more complicated. Just so that for completeness, we know how these guys come about. Okay, I have, right, some 10 minutes. Okay, I always like to wrap it up. Let me show you what we'll do next time. So now we're going to go to second order equations. And eventually we're going to see, maybe next class, how we integrate our famous undergraduate wave equation, UTT minus c squared uxx equal to 0, and we get D'Alembert solution, and we see very clearly domain of region of influence, domain of dependence, blah, 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 blah. But now, we're going to prepare the territory exactly to identify when a PDE is hyperbolic, elliptic, or parabolic. So do you guys remember? So let me write here. So let me put it here. Look, second order PDEs. If I write it like this, equal to D, where at first we can say that A, B, C, and D excuse me, are functions of x, y, u, ux, ui. Okay, so it's not necessarily a linear problem. So I can ask, when is this problem hyperbolic, elliptic, or parabolic? Remember that the way it's written with this A, but it looks like a second order almost, equation, there's this discriminant, just like when we find roots, that will determine which class it is. I don't remember when I was an undergraduate, I knew how to use it and I knew the discriminant, but where the discriminant kind of comes from, right? So I don't know if it was shown to me. Of course, when you learn this as an undergraduate, you learn more separation of variables and so on. Now we'll see why. Okay, so take the curve, gamma, P, well, we have our Cauchy data with additional data, which is, and now because the problem is second order, we are given these conditions that we had to look for in that other case, right? So this is the gamma projected curve where I have this Cauchy data, second order. So from the strip condition, we had this. We would get this. But we have to be careful. And the reason is, in that previous problem where we used the strip condition, these two guys here were not given to us. We had to find them, and once we found them, they were compatible, blah, blah, blah. But now, since all these are given to us, right, we might have trouble satisfying these things. Okay? So a note I have in the notes is a note in the notes is this. So we have to be careful. So these cannot be arbitrarily imposed. Usually, so as a comment, and I think you will see this better. Maybe I don't know if this class more not like next class. Usually, we can impose. Impose is poorly written. U equals to H of S and du dn where the n is normal to the to gamma. And you see that these two guys are coming in and so on. Because, just remember, before, in the nonlinear problem, right, first order nonlinear problem, we were not given P and Q for the eigen equation, but said, oh, come on, we have to work and find it. So we would find it from the strip condition that uses exactly this condition here, right, in the initial PDE. Now, because the PDE is second order, and I'll need to integrate it, say, twice if this is time, I am giving these conditions here, okay? And who guarantees me that, I was given good conditions? So to satisfy this, or another way to see it is, one way to see it is the good first derivative, for example, is a normal condition, so that also helps us, as I say, get out of the initial curve, right? So we'll see now. Maybe I'll just sketch this for the interest of time and leave this for next Monday. one thing I mentioned to you, okay? So what will we see next time? We will see this. Remember that I mentioned, a little bit of water, that a condition for something to be characteristic is that we cannot solve locally for the high order terms in terms of derivatives. Or another way, just think Taylor series in your mind. That's a good way to remember. To do a Taylor series, I need function value here, first derivative here, second derivative here to see up to where I want to go in my truncated Taylor series expansion, right? So the similar thing, what I mean by here is the gamma, the curve where I have the Cauchy data, right? And we already saw this, that the problem, the data is characteristic, for example, for systems and so on, if I cannot get, high order derivatives and do my sort of Taylor series expansion, meaning derivatives here. Here it's the same thing. So what we'll see next time, okay, is this. I'll come back to this next time. So this is a good place where I'm going to stop. Let me just say what we're going to do, right? Or else I have to rush. So this is, I was given ux and uy along the initial curve. And I want to do my Taylor series approximation of the solution, which is like a local construction of the solution. So I need u here on gamma, u of x here I was given, u of y here I was given, because now it's a Taylor series in two variables, x and y. But if I want to get the next term, which is uxx at gamma, uxy, and let's admit that everything is smooth so that uxy is the same guy as this guy, okay? And uyy, if I want to get this, I should be able to solve this linear system of equations, right? Because this is just p prime, q prime. I know this, I know this, I know this, I know this, and I need to solve for the other guys, right? And we will see next class that this leads, let me write here, and then that's the point where I really will finish. This leads to the following determinant. I mean, I have to complete this. We're not finished, okay? We're not finished, but this will lead to this system. If this system is different from 0, then I can get my higher order derivatives. Then my initial curve gamma is not characteristic. Okay? And this determinant, after we play with it, is what will give us the condition that for being hyperbolic, elliptic, or parabolic, right? Which is the discriminant involving B and C and so on, okay, that we learn. So this is the point I'll come back next class. And then, and then I think we're going to solve the easy wave equation, see D'Alembert solution, and move on. And soon, I think, next class for sure, I will start Laplace's equation, okay? Okay, so very good. So we'll stop here.